Welcome to this presentation about Many-Affine BBOB problems. If you're watching this, then you are likely already familiar with the BBOB function suite, but just in case, BBOB is a continuous, noiseless, single objective problem suite consisting of 24 functions that are all designed to have specific high-level properties. So for benchmarking numerical optimization methods, they're very useful because you can run your algorithm on a sphere and get quite different kind of information than when you run it on a more rugged multimodal function. And by having 24 functions with different designs, we can gain a lot of insight into how our algorithm behaves. And so last year in 2020, there was a presentation at PPSN by Diederick and Vermetten that proposed making new problems based on the existing suite of BBOB by taking weighted combinations. So just taking alpha times the first one, 1 minus alpha the second one, with some kind of weight 0, 1, with making sure that the optimum is aligned, so that we know the optimum value for calculating things like precision and for easy comparison performance. And they analyzed these landscapes using exploratory landscape analysis, which shows that using this kind of approach, we can relatively smoothly transform one problem into another one. And that's of course a very useful step, because now we can get problems that are not quite one or the other, but they have some features, which would be very useful to have for testing things like generalizability, for example. Because we can train on the pure functions and do testing on functions that are not quite those, but they're affine combinations instead. So we took this approach and we added a few modifications to allow for this Many-Affine BBOB suite. The first one is scaling of the BBOB problems, where we decide to go from the linear combination that was made by the original paper to a logarithmic one. So we take a geometric mean instead of the original arithmetic mean. And we do this based on precision. So we subtract the function value of the optimum, so we have a global optimum value that's always exactly equal to 0, which makes it a lot easier to aggregate results from different affine combinations together. And then on top of this, we introduce a scale factor, and the scale factor we determine based on random sampling, where we get one factor for each component function, because we notice that the scale of BBOB problems can vary quite significantly, even if we use this logarithmic weighting. Then by adding a scale factor, we make it so that our function scales are a lot more easy to work with. So we tried out a few different settings that you can see here, 5 different ways of doing aggregation, and we selected one of these to give us some nice resulting scale factors. So that's one change. The second thing is we changed the way that we deal with the location of the global optimum. And particularly, we want to still make sure we know the location of the global optimum. So all of the component functions are moved to one location, which is the same that was done in the original paper. Although there, they pick the location of one of the component functions as being the location of the global optimum. And that introduces some bias, because not all functions can have their global optimum anywhere in space. So in order to remove this potential bias, we sample the optimum uniformly in our domain, and that results in different functions again, where the optimum is distributed uniformly, which is quite a nice property to have for a new benchmark set, in our opinion. And then as a final modification, we changed the way that we actually sample random functions, because originally this approach was proposed for combining 2 functions, because we can then still roughly understand what's happening. But if we want to be more general, then it's nice to be able to combine many functions together. So we change it so we can get weights for each of our 24 functions. But of course, combining 24 functions is too much. We will always have some amount of multimodality, for example. So we introduce a weighting scheme with some kind of threshold. So we bias towards using around 3 or 4 functions only, instead of using all 24. So we change from something that is always very highly multimodal to something that is a bit more nice and a bit more varied. So these are the 24 changes that we make, and this results in our MA-BBOB suite. We then plug this in to our benchmarking platform, which is called IOH Profiler for benchmarking numerical optimization. And we plug in a set of optimization algorithms so we can easily do experiments. So by plugging this toolbox, this suite of Many-Affine problems into an existing toolbox like IOH Profiler, we gain the ability to do easy analysis and comparison and logging and all of these things. So we have easy accessibility of the suite, and we don't have to start from scratch to build all this. So we can take existing algorithms, plug them into the functions via IOH Profiler, and get interesting results. And in particular, what we wanted to look at is how we can test automated machine learning methods. So that's our basic use case. We wanted to see if this can help us test things like generalizability of algorithm selection. So a very basic setup we take is we just take 1,000 randomly sampled MA-BBOB functions, a portfolio of 5 different numerical optimization algorithms, and we do some initial testing. We just check first the ranking of these algorithms on each of these two suites. So we can see on the left the rank distribution on BBOB, and on the right we see the rank distribution on these affine combinations. And we see some changes. We see that, for example, for the green algorithm, Carola, it's quite a lot worse on these affine combinations, which we can explain by looking at the multimodality of these problems, which it cannot deal with very well. But overall, we see there's quite some overlap here. So this is something that it's not changing the underlying distribution completely. So in principle, we would expect that we should be able to somewhat generalize from BBOB to the affine combinations. It's not everything swapped. So given this, we then make a very basic algorithm selection based on exploratory landscape analysis. And as a comparison, we also make the same algorithm selection based on the used weights, because we inherently have a new representation of our functions, which is just the vector of weights that each function is using. So this gives us 2 different representations, so we can compare how they work by looking at the cumulative loss. And if we look at that, then we see that just only cross-validation loss is quite good, no matter either but using weights, which is here in red, or exploratory landscape analysis, which is here in orange. Both are performing okay, but we do lose quite a bit when moving to ELA. And in terms of generalization, which is the green and the blue one respectively, we lose quite a lot more performance there. So if we train based on weights, where we only have the vectors 1 and all zeros as our training data, that generalizes quite a lot better than doing it based on the exploratory landscape analysis, which is quite an interesting finding in our opinion, because it shows that we now have a test bed where we can actually analyze what's happening with these features in a bit more of a fair way. Because with this kind of function generator based on the popular BBOB suite, we are no longer limited to just these 24 very different functions, and we can hopefully gain some new insights in testing automated machine learning methods. And we did some basic exploration here of generalizability of an ELA-based algorithm selector, and show that this might not be perfect. And this is just a highlight of something we could potentially do with this suite. We have tried to make it as easy to access as possible, and we hope that this is something that allows us to gain some new insights into automated machine learning and how that can be used in the context of numerical optimization.